Hello and welcome to the second video of Section 2.8 Related Rates. This video has three examples of related rates involving three-dimensional geometry. In this course, we expect students to be familiar with basic area formulas as well as trigonometry. We also expect students to know the formula for the volume of spheres, prisms, and cones. Any other geometric formula that is necessary will be provided in the problems. Our first example involves a cube. The volume of a cube is decreasing at a constant rate. At what rate is the surface area changing? Challenge yourself. Pause the video and work the problem before continuing. Be sure to diagram. We begin by diagramming a cube. Our first question: there are no constants, and we have three variables, v for volume, s for surface area, and x for side length. Our second question: we're given the rate of volume change with respect to time, dv dt is equal to -4, and we're searching for ds dt, the rate that the surface area is changing. 3. We need two equations to connect volume and surface area in a cube. The volume is equal to the side length cubed, and for the surface area, a cube has 6 sides, each of area x squared. So the surface area is equal to 6 times x squared. 4. We differentiate both equations with respect to time t. Our goal is to calculate ds over dt, the change in surface area with respect to time, and we are given information about dv over dt. Manipulate the equation, divide both sides of the first equation by 3x squared, and substitute for dx over dt. And cancel. Now, we're told that dv over dt is constantly -4, so the change in the surface area depends upon the current size of the cube. This is the best answer we can provide with the information given. Once we're given a specific side length x, we can figure out ds over dt. For example, if the side length is equal to 4 centimeters, then the change in surface area is -4 centimeters squared per minute. Our second example involves a cone. Challenge yourself. Pause the video and work the problem before continuing. Don't be fooled by the constants provided in the problem. If you read carefully, the constants are for the cup, but the problem concerns the water. There are no constants for the water. And for the variables, v is the volume of the water, r is the radius at the top of the water, and h is the height of the water. 2. dv over dt, the rate of change for the volume of the water, is 2 cubic inches per second. When h is 2 inches, we are to calculate dh dt, the rate of change for the height of the water. 3. The water takes the shape of the cone, and the volume of a cone is 1/3 pi r squared h. Differentiating with respect to t and being careful to use the product rule on r squared h, we relate the rate of change for our three variables. Now, we have information on h and dv dt, but we are left to calculate, if possible, the values of r and dr over dt. Fortunately, we can use the geometry of a cone to help us along. A cone can be formed by rotating a right triangle 360 degrees through its base. Notice the right triangle that r and h make. The triangle of the water is similar to the triangle of the cup, and the triangle of the cup has side length 4 and 11/8. We can use this similarity to find the relation r over 11/8 is equal to h over 4. Cleaning that up, we obtain r is equal to 1132 times h. This relation really belonged in 3. Before moving to step 4, we can remove the variable r from our main equation, so our main equation no longer has r in it. We have a horrible constant, but v is really connected to h cubed. Let's begin step 4 by differentiating with respect to t. And we obtain a beautiful equation, certainly easier than the equation we had a minute ago. And we have exactly enough information to solve this equation by just plugging in 2 for dv over dt and 2 for h. The rate of change for the height is 512 over 121 pi. Our third example involves a triangular prism. Challenge yourself. Pause the video and work the problem before continuing. Again, don't be fooled by the constants provided in the problem. If you read carefully, most of the constants are for the trough, but the problem concerns the water. The water has a constant length of 20 feet. The variables will be volume, height, and width. 2. We are given the rate of change for the volume, and when the water is 2 feet deep, we are trying to find the rate of change for the height. Let's be careful with the equations that we find. There's the obvious volume, where we're working with the volume of a prism, where its length times the base area. The length is 20, and the base is a triangle with sides h and w. We also have a similar triangle. The triangle of the water is similar to the larger triangle of the trough. We can use this similarity to find the relation W over 3 is equal to H over 3, or just W is equal to H. We combine the two equations to find a main equation, V is equal to 10H squared. We differentiate the equation with respect to t, and we have all the information that we need. dV over dt is 12, and H is 2. And we find that the rate of change for the height of the water is 0.3 feet per minute. Hopefully you're becoming comfortable with related rates. Be sure to strengthen your understanding through practice.